Okay, this is our first question. So here we are given two Fourier transform pairs. You can see it. And we have to prove these two identities. And this expression, these transform pairs are called modulation theorem. Okay, so you can see that here we have time domain signal. Actually, it is a product signal, no? Xt, the signal xt is multiplied by cos omega naught t with another sinusoidal signal. So this is a product signal. And we have to find the Fourier transform of this time domain signal. Okay. So in another word, we are asked to find the frequency spectrum, okay, or frequency domain representation of this signal. Okay, so we will see it. So if we consider the first identity, if we consider the first identity, so first we will consider this one, first identity. So we are given xt, this is any time domain signal. Okay, this is a time domain signal, unknown time domain signal. Okay, and it is multiplied by cos omega naught t. So this is the fundamental angular velocity, angular frequency of this sinusoidal signal. So we have to find the Fourier transform of this product. Okay, so let's see how to do it. Okay, so you can see that we have given an identity inside here. It is not mentioned, but we have given a fact, that is, if we have any signal xt, time domain signal, if we get the Fourier transform, okay, it is capital X omega. Okay, so if we get the Fourier transform of xt, we will get the frequency domain signal, that is x omega, capital X omega. And if we get the inverse Fourier transform of this capital X omega, we will get the time signal xt again. Okay, so this is a fact. Okay, so we will try to do this. So here we have to find the Fourier transform of xt cos omega naught t. Okay, so I think you can remember the expression to evaluate the Fourier transform. Okay, that is, if we have xt signal, okay, if we get the Fourier transform of xt, we will get capital X omega, and it is defined as integrate from minus infinity to plus infinity xt, this time domain signal xt, multiplied by e to the power j omega t dt. Okay, so this is the identity for evaluating the Fourier transform or frequency domain signal of any time domain signal xt. Okay, so you can see that here t is a variable and omega is also a variable, but we do this integration with respect to t, so we can consider this t as a constant. Okay, so if this integration is with respect to t, so we can consider this omega as a constant. Okay, omega as a constant, this t is the independent variable. Okay, so if we do this integration, we will get a function, get a expression with t and omega. Okay, then if you apply this limit minus infinity to plus infinity, instead of this t will be vanished, and we will get the expression only with omega. Okay, so that is the frequency domain signal. Okay, so this is how we evaluate the Fourier transform of any xt signal. So you have to remember this identity. Okay, so we can use this identity to prove this. Okay, so here I apply it. Okay, for this signal I apply it. Okay, so we have to find minus infinity to plus infinity. This is our signal now. This product signal is our signal, no? Time domain signal. So instead of xt, here we have xt cos omega naught t. Okay, and you have to multiply it with e to the power minus j omega t dt. Okay, so what we have to do, we have to evaluate this integration. Okay, so you can see that here we have a cos term. Okay, here we have a cos term. So when we do an integration, and if we have this exponential term, and also if we have sinusoidal terms, we can convert the sinusoidal into exponential terms using well-known Euler formula, no? Using a Euler formula. Okay, so you can convert this sinusoidal terms or sine terms into exponential terms, so it would make this integration easy. Okay, so we will do this. Okay, here we have cos omega naught t. We can write it as half e j omega naught t plus half e minus j omega naught t. Okay, so I hope you know how to get this. Okay, so here if we have cos theta, sorry, if we have e j theta, we can write it as cos theta plus j sine theta. And if we have e minus j theta, we can write it as cos theta minus j sine theta. So if you add these two equation, you will get, if you add 1 by 2, 1 with 2, you will get 2 cos theta is equal to e j theta plus e minus j theta. Okay, so cos theta is equal to half e j theta plus e minus j theta. So I will get this, I will apply this identity directly to here. Okay, so you will get these terms. Okay, so if I write this integration again, so I can write it like this, minus infinity to plus infinity. So xt is there, xt is there. Now instead of this cos omega naught t, I can apply this exponential terms. No, I can substitute. So I have half e j omega naught t plus half e minus j omega naught t. Okay, and also we have e minus j omega t. Okay, so I can write this again. So here we have a plus value. So I can separate this integration into two integration, no, because the plus value is there using the linearity property. Okay, so using linearity property, I can write these terms and these terms separate, this integration and this integration separately. Okay, so this term also multiplied by e to the power j omega, and this term also should multiplied by e to the power minus j omega t. This term also multiplied by e to the power minus j omega t, this one, and this one also should multiply it by e to the power minus j omega t. So I will write it, I will do these two things at once. Okay, I hope you will not get confused because these are some basic mathematics. Okay, so here we have minus infinity to plus infinity. So half is there. So I can get out this half, okay, because it is a constant. So I will get half here. So xt is there, okay. So this xt is there, and e j omega t, and it is multiplied by e minus j omega t. So I get this e minus jt out. So I will remain here. I get minus jt. So here minus jt. So plus omega will remain here. And here I get minus value. So here I have to put the minus value. So here we have omega naught. Okay. So this is one terms, and in same manner, I can write other terms as minus infinity to plus infinity. So xt is there. Okay. So here e to the power minus j omega naught t, e to the power minus j omega t. So I will get e to the power minus j out. Here I get minus j. So here minus j came out. So omega naught is there. And here we have the omega dt. So I will get these two expressions. Okay. So you can see that if we consider these terms, if we consider it as a capital omega or something, capital W or something, let's say capital W for this omega minus omega naught. Okay, so you can see that this omega is a variable, no? This omega is a variable. This t is also a variable, but with this integration is in with respect to t. So we can consider this omega as a constant. Okay. So anyway, this omega is actually a variable. So you can see that if this omega is varying, this w also varying. Okay. This omega is varying to minus infinity to plus infinity. This w also varying minus infinity to plus infinity, but with a little shift. Here we have only a shift. Okay, but this is varying, and this omega is also variable. Okay, so I will get this term. Okay, I will get this term separately. Okay, so if I write this like this, minus infinity to plus infinity, x t e minus j omega minus omega naught, instead of omega minus omega naught, I substitute capital W t and dt. So I will get this expression, this kind of expression. Okay, so you can remember that this is our Fourier transform identity, no? So I will write it again here. Okay, if we write the Fourier transform of identity, okay, if we have a signal xt, if we get the Fourier transform, we will get capital X omega, and that is equal to minus infinity to plus infinity x t e minus j omega t dt. Okay, so what you see here and here, it is the same expression. Only here the simple omega is there instead of simple omega. Here capital W is there. Okay, so here you can see that if we do this integration and apply the limit, you will get the function with omega. Okay, with omega, and it is denoted with capital X omega. Okay, so here also, if we do this integration, okay, and apply the limits for this t, again you will get capital X, same capital X with capital W. Okay, so same signal you will get, but only different is here you have omega, here you have capital W. Okay, so what is this capital W? It is omega minus omega naught. So you will get this expression if you integrate this. Okay, correct. So I think you can understand this. Okay, so here this term we can write as, okay, we can write as half capital X omega minus omega naught. Okay, and here the plus is there, and in same manner, if you consider this part separately, this omega naught plus omega, also we can consider it as another omega 1 or omega 2 value. So you will get the expression with capital X omega 1 as in this case, okay, same manner. So here omega capital W1 is omega naught plus omega. So here you have half X omega plus omega naught. Okay, so you will get this expression. Okay, so you can see that if we find the Fourier transform of frequency domain representation of xt cos omega naught t, okay, we will get this function. No, if we get Fourier transform of x t cos omega naught t, we will get this expression. Okay, so our first identity is proved. No, so this is proved. Okay, so in the same manner you can prove this one also. Okay, so you can do it as a homework. So do it as a homework. So this identities is called modulation theorem. Okay, so when you are so in this communication system subject, sometimes you have to find the frequency spectrum of modulated signal. Okay, frequency spectrum of modulated signal. So you can use this theorem directly there, if you can remember this. Okay. So you can see that in AM, FM also we are using this theorem indirectly. Okay, so you can see it in future. So this is that. Okay, so if you can remember this okay, so I think you get this. Okay, so also this can be interpreted using we have some properties in Fourier transform, like frequency shifting property, linearity property, like that. Okay, so using this properties also we can find this expression. Actually this xt is multiplied by e minus j omega naught t, you will get x omega by omega naught. So this is called the frequency shifting property. Okay, so this is the frequency shifting property. Actually in this part, okay, in this part from here to here, we prove that frequency shifting property also here. Okay, so if you can remember it. Okay. Okay.